Hello, welcome back to Hardware Design. Sorry I didn't really advertise, so I suspect that most people will be watching. So what we're going to be working on this week is a QuadRoot module. So the idea is that I need I have a project right now where right now I need to calculate a bunch of parametric line intersections with other lines, and the sort of easiest way to do that, or the naive way to do that, is with calculating a large number of quadroots. So since this is going to be a reoccurring unit, I thought it would be worth playing around with. So we'll need to give our module a name. So we'll call it QuadRoot, and then there we go. Maybe make sure the font's a little bigger. That seems like a pretty reasonable size. Alright, so let's get going. So this is quadroot.vp implements quadratic equation. So opposite of b plus or minus square root of b squared minus 4ac divided by 2. So we need a few things. So 2a. So this is kind of an interesting function because sometimes it will have one output, sometimes it'll have 0 outputs, sometimes it'll have 2 outputs. So we need some way of indicating that. In the application that I'm interested in, it doesn't actually produce. I'm not actually interested in the imaginary roots because an imaginary root doesn't correspond to an intersection. But let's give him name. Good. So let's see. So we're gonna make this combinatorial. Let's keep it simple. We'll just call them A, B, C to match what we're expecting. Excuse me. Play the normal trick of having a parameterizable bit width. We'll do A, B, C. There we go. Output logic. R1. Just count from 0, so R0. R1. And then we'll add this valid tag. So that way, if the root doesn't matter, or if that root specifically is not the one that we're interested in, then that will be that. Cool. Then we need an end module. Great. And then we used a parameter that we haven't really defined yet. Move all these over so that the columns line up. So my $BW equals parameter bit width name. We'll say the value is 16. Do we want to make this fixed function? I mean, not fixed function, but fixed point. So, yeah, this would probably be more helpful as a fixed point unit. What we'll actually do is we'll say integer width, and we'll say fractional width. So what we're going to do is we're going to represent it as a integer width, and then we'll say the value here is 8, and parameter name. So fraction width, we'll say value is 8. And then we should change the default here to be $IW plus $FW. So the idea is that instead of having a 16-bit integer where the radix is to the right of the LSB, we can specify how many bits are integer bits and how many bits are fraction bits. So in this case, we're going to say that we have 8 bits of integer and 8 bits of fraction, so the total bit width is that, and then we'll just keep that throughout. Maybe later we'll come back and it would be worth tweaking this output precision to land on something better. All right, let's make our lives a little easier. So we're gonna get rid of this, and we'll make a little note here. I'm going to assume that A is always 1. Good, so now we have B and C. So B times B. And clearly this. So if we do a B times B, the result is going to be an IW plus IW plus FW plus FW bits. So if it was an 8 under 8, it is now going to become a 16 by 16. Good. And we'll have AC, right? A times C. And again, this is exactly that many bits, which is good. So we don't need to do any sort of rounding to make sure. And since we provide an interface like this, it's probably for the best. Let me scroll up here to make sure I'm not missing any comments in chat. So that's that. All right, so then what we're interested in is the calculating this guy. So we're just gonna carry that along to help us out. So we already made a mistake. So A is always 1, so AC is just gonna be C left shifted. And how much do we left shift by? Well, it's going to be 2 because that's the 4. And then we also need to align the fraction bits. So we're going to also left shift by FW. Great. So now we can declare these. We'll say they're logic. In both cases, it should be 2 times BW minus 1. So 16-bit things become 32-bit things. That was AC. And B squared. So we'll call this like 4AC. There we go. So then we're interested in their difference. And I think we'll make our lives a lot easier if we make everything signed. So I'm just looking to see, where do I put that? So it goes after the bit specifier. So we're going to do this. Now life is easy. So now we have signed multiplies inferred here. We should make sure this is signed as well. Boo. Signed. Signed. Great. So this is now a signed multiply. This will be, and then we mean this to be arithmetic. So that should happen that way. Great. So we can record their difference as being b squared minus FAC. Great. So that is also and then technically it could get 1 bit bigger. So we're going to do that. So now diff has 1 bit. So this is, in terms of bits, 1 plus IW dot FW plus FW bits. So here's where we can ask the question, you know, we can say, well, so let's say that R1 valid is always going to be our second root if we're having a second root, and the only way we have a second root is if diff is greater than 0. Seems fair. And R0 would be valid if diff is greater than or equal to 0. So we should probably define these as real numbers. So diff was +1, tick D0, there we go. And then we need to do a square root. So we don't want that. We want that guy. So it seems to. So do I already have Firefox running? I do not. So what I am pulling up are the descriptions for some units. So I think it should be happy. So I have another session open with all of the things. There we go. So we're not actually going to build a square root unit. It's way faster to just use one of the built-in ones. So since we're using the Synopsys toolchain, we can just directly use that. So let's see what we got. So that's FP square root, ARB square root, pipe, DW square root. So we'll do this one now. So we'll do direct instantiation in Verilog to make our life easier. And TC mode. So that's how we instantiate. So this gets the diff root, the reticand width is this. That's probably overkill. Ooh. Oh. GoCool is following along. For the RZO valid, why did you make it 2BW plus 1? Oh, so diff. So the question is, when I'm doing this assignment of R1 valid and R0 valid, and I have diff compared to 0. The question is, why is 2 times bit width plus 1 the bit width instead of maybe something like 2 times bit width? And the reason is that in this step, when we did diff, b square minus FAC, so BSQ is 2 times bit width bits. And so if you perform an additive operation on 2 things of the same width, so these are both bit width, the biggest result is going to be one bit bigger. So this is 2 bit width plus 1. And so the constant, in order for the constant to match in precision, it needed to be 2 bit width plus 1 tick D0. Though I suspect that since I'm doing 0, if I had written like 5 D0, it would have been fine. And how would we mitigate square root without direct instantiation? And what are, yeah, so that's an excellent question. So this unit is very expensive. It is roughly going to be somewhere between 1/2 to 2x times the bit width more expensive than a multiply. It's, so the thing to think of is that it's maybe an order more expensive than doing a multiplication. And so these are things that you should be very careful of implementing. And so there are a few ways that we can mitigate the cost of these units. And so let's work through a few of them. So the first way that I see a lot is that generally people are going to want to do something like radius squared times a squared plus b squared. And so their immediate impulse is to transform this into, okay, well, r is greater than the square root of a square plus b square, and actually make it sort of like this, like a times a b times b. This is kind of silly. You were much better off leaving it r times r is greater than 8 times b, and then not do the square root, because you were going to save some math there. The other way that you might mitigate this is that this is a fairly common thing. If you're going to do a 1 over square root of x, a divide is also very expensive. Maybe not orders of magnitude expensive, but still, you know, fairly expensive. However, this whole thing can be evaluated using the same implementation as a square root, just slightly different changes in constant. So this is actually usually a unit that would be available in the library. So this is a list of the cells. So yeah, so there's a reciprocal square root unit to solve these problems. The other place that you might mitigate this is, so oftentimes what we talk about is, so the first trick was, you know, leave things in squared magnitude. The second trick is fuse complex operations to amortize the cost. The third trick is to change the algorithm. So in this case, I am assuming that what I am interested in calculating are the intersections of quadratics with lines. So this is going to go into a font renderer. The idea is that the surface of a font is represented by quadratics, and so if I'm interested in calculating the overlap of the font, the glyph, with the pixel, what I'm going to do is I'm going to find the intersections of the quadratic with the boundaries of the pixel and then integrate those regions. So the other approach to do this would be, instead of calculating analytically the boundaries and then analytically integrating, there's another algorithm where we might be able to do a slightly larger number of multiplications by projecting the samples into a higher space, and we could avoid the square root entirely, or at least maybe, I think in this case I'm going to need 8 square roots. I mean 8 of these units, and I have 8 square roots, so I might be able to get rid of 7 of those 8 by changing the way that I evaluate the broader problem. And so from a broader design perspective, this would be one of those things where if my application expert came to me and said, I really need a square root, I might push back and ask, well, is there a way to do this with just more multiplication, or, you know, a change in type or a change in domain? You know, is there some way to get rid of this? All right, so if I shift to log space, the square roots get a little bit easier. You know, could I do everything in log space instead of in linear space? You know, those are the kind of questions we might ask. But yeah, the third trick is usually just try not to do that. The other thing is that I wouldn't be scared of the square roots up front. If somebody's asking for a square root in their algorithm, it would be good to quantify that cost. So if we're, you know, we'll spend the next couple weeks fiddling around with this. So if somebody, one of the things we'll do is we'll actually measure how expensive the square root is, and if we think we're really getting burned, we'll ask some hard questions. I mean, one problem is, and you could probably guess that we're going to have to do something about it, is that a square root has a lot of delay. So we're probably going to look for piped square root. Yeah, square root under pipe. So there's a stallable pipeline square root module. So we're probably going to end up adding clock and pipelining our module to better support what's going on. Cool. And then let me kill my other VNC in case that's eating up bandwidth. But no, that's a good question. Is that these things will will be expensive, and in this case, it's really expensive compared to some of the other math, because our multiplies were, 16-bit. Our addition was, but after multiplying, we got 32-bit numbers, and so now we're doing a 32-bit square root. So this could potentially be really expensive. So one of the things that we may actually want to do is parameterize everything and actually round after we multiply, or round after we do the subtraction, to avoid doing this, because maybe we don't care too much what the exact number is. Downstream in the algorithm, it may not matter. So we want to fiddle around with all these precisions just to play it. But right now, what I'm doing is I'm trying to preserve as much of the precision as possible, so that at the last step, when all I have to do is throw away bits, and then that's where all of the error is. Cool. So let's see. So yep, we're going to turn on 2's complement. Actually, we could turn off 2's complement mode, because I don't think it matters. So if we're negative, the number shouldn't matter. All right, so here's where things get interesting. So let's take a peek at the notes for square root and see if they, so they always radicand with +1 divided by 2. Okay. We're going to copy that right there. So we're going to logic signed. So it's bit width. So it's 2 times bit width plus 2 divided by 2. So this is carrying everything through. We can get rid of that. That becomes a 1. That goes away. Then we're going to subtract 1, so that goes away. So now we're back to bit width. Great. Bit width :0. Then let's move this further up. So let's see, coming back, so the question in the comments is, coming back to the first question, isn't BSQ having a bit width of 2 BW, so one more should be TBW plus 1. But if we have TBW plus 1 : 0, it's TBW plus 2 bits. No. So I don't necessarily, don't worry about double asking questions. All right, so these are each 2 BW bits. 2 BW bits. 2 BW bits. And then the way that we've defined this is that this is 2 times BW, and then we're omitting the -1. So this is equivalent to 2 BW plus 1 bits. And so this would be BW plus 1 bits. So if this is 2 times BW, that's 2 BW plus 1 bits. And so to make sure that this constant is the same bit length, it would be 2 times BW plus 1, as opposed to, and this is because this part of a constant says how many bits are in the constant, whereas this says this is the first index in the string. So I think that's usually where I get confused, is that that's what happened. Hopefully that answers the question. All right. Oh, great. So that answered the question. So we have our 0 valid, we have our 1 valid defined. Great. So the last thing to do is we need to do the opposite b plus the diff root and we need to do minus b minus diff root. All right. And we will go ahead and set those straight to R0. Sign R1 equals, great. All right, so now we need to make sure that we aren't hurting ourselves here. All right, so diff root is BW, and it is 8 bits of fraction, 9 bits of integer, minus B is 8 bits of integer and 8 bits of fraction. And then we do not know if B, great, so this makes sense. So the only issue with this statement so far is that there are too many leading bits. The issue is that so we have a 17-bit thing and a 16-bit thing added together, which is technically an 18-bit thing. So we're just going to call these R0 long, R1 under long, and so we will need new versions. Clicked off the screen. R0, we said long, R1 long, and then we said if it is 16 bits, that it needs to be 2 extra bits. Good. And what I'm trying to avoid here is that as it's running synthesis, generally it's going to be looking at this, making sure that these bit widths are close to each other, that the bit width of this is appropriate for the resulting number here. So if we make this too short or too long, it'll complain at us, and I suspect I've already missed something. But like I think I need to 0 extend. Yeah, we'll just add a note here. May need to sign extend B. May need to sign extend B. Great. Now, since we are doing signed arithmetic, it should be okay with what we're doing. R0 under long, and then we want to grab $BW minus 1 colon 0. And we want to do the same for R1 long. Great. So this is drop leading bits. And then I think we forgot the divide by 2. Yeah, I did forget the divide by 2. All right. So we're going to make the divide by 2 implicit. By skipping the bottom bit. Great. So I think this is good, and we're gonna keep this short because I have more meetings after this. But so I think next week what we'll do. So next week on hardware design, we will we'll write the test bench and verify. And then the thing to do after that is test to evaluate the cost. I'm sort of curious how much these square roots go by. And the way we're going to do the verification is pretty simple, is that we should be able to generate, gen, B, and C with random. Then we should be able to check R0, and it should be something like R0 times R0 plus B times R0 plus C should be exactly equal to 0. In this case, I don't think we've dropped any bits, but it'll be interesting to see how far off we are. I suspect I've done something hinky here that will probably mean we aren't exactly 0. Which would be upsetting. All right. So we'll call that it for today. And I will see you all next week. Have a great Wednesday night.